Oh, hell yeah. Alright, here's the next problem. You know, to me, we did this one, stopping distance. And as a function of acceleration, we got that. And as a function of reaction time. You know, to me, you're just going to be cruising along, and if you don't do nothing, your distance is still that initial, that velocity you're going times your anyway. So the same thing here. Now we need to be a traffic engineer. You know, to me, I think we'd do a way better job. Never mind, we shouldn't get into that. But holy Toledo, I live in a town where it just don't make no sense. But anyway, so we want to know how long a yellow light should stay on. You know what I mean? So it's the change in time. Basically just the time for the yellow. But they're going to call it the change in time. You know what I mean? The second the yellow turns on, flash, 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 and then the second that it, you know what I mean, turns off. That's going to be the change in time. Anyway, I think we can do this one a lot faster. But it says, hey, we give you an equation. Is this right? Can you show that this is right? You know, screw that. We're going to do the second part. It's the easier one. We have a 16-meter intersection. Oh, and I have to start my clock. Damn it. Well, we'll just go for it. Hopefully, we'll totally screw ourselves over. But check this out. This is in 60 kilometers per hour. This is the first one, just right off the bat. It is ridiculous. We need everything in meters per second. That's why if you're going to do any physics, don't use English. Just use meters per, even kilometers per hour. Hell no. So we'll just go over here and do 60 kilometers, 1 hour. So 1 hour, we're going to cross those out. 1 hour is equivalent to 3,600 seconds. Hell yeah, that's the fastest way to do that. 1 kilometer is 1,000 meters. Hell yeah. So we're gonna 60 times 1,000. 60,000 divided by 3,600. So it's 16 point, you know, who cares? 16.7 meters per second. There you go. Done and done. Okay, so yeah, so that's our speed. The other information, we have a reaction time, change in T. R is 1.1 seconds, Q. And then we have an acceleration of -2 meters per second squared. And it is a physics book, so they want you to use 3 significant figures. See how we used 3 significant figures right there? Good enough. Okay. And now what? I have no idea. But let's say you were just going 16.7 meters per second. How long is it going to take you to get through this intersection? Well, if the intersection is 16.7 meters, it's going to take you 1 second. But it's only 16 meters, it's going to take you less than a second. Well, so now we can figure that. So if we got... And if this is meters per second, how do we get seconds? Well, you need to get seconds to the upstairs. So you actually probably need to divide by this velocity. Okay, so how about this? This is meters. How about divide by meters per second? There you go. Seconds is upstairs. So we're going to take 16 meters, divide it by 16.7 meters per second. Seconds goes upstairs. And then we got... I'm going to store this, you know, we're going to store this as a big number x. So just in my calculator, this is x. It's just so we don't lose any of those good juices. You know what I mean? It's like cooking a roast. Okay, so now we got 0.96 seconds. Hell yeah. Okay, so the yellow light needs to at least be 0.96 seconds because by the time you get to the start of the intersection in your little car, it turns yellow. Well, guess what? You'll actually get through the intersection, if this is the intersection, you know what I mean. You'll get through in 0.96 seconds. Alright, hell yeah. I gotta keep an eye on the clock. We only got 5 more minutes, and then we gotta add some more time. Okay. But, you know what I mean? It tells you how a yellow light works. It's like, well, one, you physically have to get all the way through the intersection. You know what I mean? No one does that. I'm about right here. And it's just like, hell yeah. I'm in the intersection by the time the yellow turns to red. You know what I mean? I think that's the new rule. If you're in the intersection, by the time the yellow turns red, you're pretty much good. You know what I mean? So, but anyway, from an engineering perspective, you need to get your car all the way through. But reaction times, you know, to me, we're dinosaurs driving really fast cars, and it takes us a whole second, 1.1 second. How far are we going to go in 1.1 second? Distance is in meters, velocity is in meters per second, and you multiply by time. Hell yeah, that'll give you meters. Okay, so we're going to take that 16.7 meters per second multiplied by 1.1 seconds, and we could have done that in our head. If we're going 16.7 meters per second, how far are we going in 1.1 seconds? Well, you just multiply. Anyway, so we're going to go x times 1.1, and we get 18.3, and we'll store that as a. Booyah. So, okay, this is in meters. Okay, so our reaction time is 1.1 second. Well, okay, well, if our reaction time is 1.1 second, we already know that the yellow light has to stay on for 0.96 seconds plus 1.1 second. You know what I mean? So that would be that would be doable. That would be doable. But then here's the deal. Here's the friggin' deal. Is that I think this is kind of what they get. Like, if this is your intersection, and you're here, and here is perfect, where this is going to be it's going to take you, you're 18.3 meters away from the traffic light. Then you can get through the intersection. You know what I mean? Because by the time you actually react, you could. No, this is kind of weird. Like, yeah, if you're 18.3 meters away from the intersection, you can't even put on the brakes until you're in the intersection, or touching the intersection. Okay, so this yellow light definitely, that's why it has 3 components to this yellow light. Like, this is component number 1, this is component number 2, but you still have to add component number 3, which is farther away. So yes, yeah, the yellow light definitely, if you're traveling full speed and you get to right here, the yellow light has to be long enough to get your car over here. Now, if your reaction time is here and you can't even put on the brakes, you have to be able to get all the way through. You know what I mean? So hell yeah, it's got to be 1.1. It's got to be about 2 seconds. But then if you're literally right here, how about another? How far is this? A plus B. A plus B. So this already is 26. Oh, we're gonna run out of time. This is already 26 meters. So let's just add another 10 meters. So we're gonna say at another 10 meters. Or how about this? Let's add another 18.3 meters, because that's your reaction time. So let's say you're so now you're B twice. Oh, A twice, B. No, alpha A. Yeah, this is alpha A times 2. So you're 36.7 meters away from the just checking time. We're gonna run out of time. We got to put 10 more seconds, 10 more minutes on the clock. Okay, and hell yeah, you're gonna get to here, and so now the problem's juicy. You know what I mean? Will you be able? And then so right now you were 36 meters away. Your reaction time gets you to here. Can you stop in 18 meters? We basically want to know what the hell the stopping distance of the car. What's the minimum stopping distance of the car? Once we figure that out, then hell yeah, you had enough time to stop. And okay, so and we can just guess. Look at this. Look at this. We got 30 seconds to guess. So we're going to change our velocity by 2 meters per second every second. Okay, so if we're going, how fast are we going? 16. So we need to, we're going to go from 16 to 14. Yeah, we're going to go, oh, we're going to totally run out of time. Yeah, we're going to, 8 seconds. It's going to take 8 seconds to actually stop our car. Okay, all right, 10 more minutes on the clock, and catch you on the flip side. All right, holy Toledo. Yeah, I was underestimated. It's going to take you a full 8 seconds to friggin' stop your car. And from the last problem that we did, let's say we were just trucking at 16 meters per second, and we're going 8 seconds to stop our car. How far is that? This is going to give us the wrong answer, but it's a good first guess. 133 meters. But guess what? We're going to be going 16 meters per second, but once we stop, we're going 0 meters per second. So our average velocity is 8 meters per second, and this was 16.6. So divide by 2, it's going to be, and we're going to store that as c. So our velocity average for our stopping is 8.3 meters per second. Okay, and now we take 8.3 meters per second times 8 seconds, and times 8 is 66.6 meters. Okay, holy hell. So this distance right here has to be 66.6 meters. Because that's literally the stopping distance. Because, and then this time right here, we need to get more accurate on that. So let's break out our equation. Acceleration is change in velocity, change in time. Now this is an equation as long as this is constant. Because this is saying this is average acceleration. But if your acceleration don't change, average acceleration is acceleration at every point. Okay, and then what the hell we want to know? We want to know change in t. So we rearranged the equation. We got change in velocity divided by acceleration. Well, you're going from change in velocity, velocity final, 0 minus, change in velocity is velocity final minus velocity initial. But anyway, yeah, 0 velocity is our final. Our initial velocity is 16.7 divided by our acceleration, -2 meters per second squared. Got it. So that's going to give us our time. X divided by -2 is -8.3, and we already stored that. We stored that as alpha c. Well, but now we can put it negative answer stored as alpha c. So perfect. So negative. Our time is. Now is our time negative? No, because this is negative and that's negative. Yeah, so our time is positive. Holy Toledo. Alpha c, negative alpha c, stored as alpha c. Yeah, time is always positive. Anyway, caught ourselves before we wrecked ourselves. And now we got this. Now we have x divided by 2. Whoa, that's the same. Am I just in a time warp? So our velocity is 16.7. Is that right? Yeah, our velocity is 16.6. Divided by 2 just happens to be, it's interesting. Why is that making sense? Our change in time is, it's just half. Well, yeah, because of, oh, fascinating. Okay, fair enough. Yeah, our change in time is c. Alpha c. And then, where did I get confused? Because we found the change in time. And, if this was our new change in time, our distance is going to be 16.7 times that 8 times 8.3, and this should be positive, 8.3 seconds. Okay, so we got alpha c, no, x, and then, sorry, x and then alpha c. That's 16, so we multiply those two together. Yeah, and you get 100 and but this had to be divided by 2. Yeah. So we got x divided by 2. What the hell? X divided by 2 times alpha c is 69.4 meters. All right, new number, 69.4 meters. So this is our minimum stopping distance. Oh, we're still going strong, I think. Hell yeah. Our reaction time is 18.3 meters. Our actual stopping distance is 69.4 meters. And our intersection is 16 meters. So this is 16 meters. Okay, cool. So this says if we are 69.4 meters, we could just stop, but our reaction time has to add another 18.3 meters. Now, is that time right? Yeah, because we have, this is our velocity times 1.1. Hell yeah, 18.3. We stored that as, yeah, and that's alpha A. Cool. Ooh, we're really tight. We shouldn't be doing this. We should be grabbing a new sheet of paper and stuff. But it's interesting, trying to cram it all in. Can we actually get to the friggin' answer yet? My goodness. So what's our time? So the time that the light, yeah, so if we're way out here, we have to, if we're way out here, we should be able to, oh yeah, because if we're out here, we could just stop, just barely. Because it takes this distance from here. Once we apply the brakes, we will barely stop right there. So, and this is our reaction time. We don't even do anything through here. So if our car is anywhere closer, we're going to stop in the intersection, hands down. So the minimum that the light has to stay on is for, hey, I see the light, and I better be able to stop. And so we're going to have 1.1 seconds. The time it takes to stop right here, which was just, we figured out the distance, but we really didn't even need to figure out the distance, just the time. And that was going to be, well, it was going to be this, 8.3 seconds. So we got 1.1 for reaction time, plus 8.3, plus the additional time, had you have been just in here, you still, like, you can't stop in the intersection. You have to get through the intersection. Oh, actually, you'll probably just use this. Because if this is a reaction, it's just going to be basically this. 8.3 plus 1.1. 8.3 plus 1.1. See, now I'm getting confused because this is 9.4 seconds. Had you, oh, this is fascinating. But like we said, if you're just right here, you have to continue through the intersection. But check this out. If right here you say, oh, I can't make it and I'm just continuing, you won't decelerate. So you'll still have your initial velocity from this position, whether you choose to brake or whether you choose, you can stop right here at this point, or at the same point, you should be able to get through. So there's a point where, yes, you could stop, and yes, you can get through. So that's what this problem is all about. That's what I think. And that point, but you're not going to slow down. You can't do your reaction time, slow down, and then crawl through the intersection. Hell no. You just have to not brake and just keep going through the intersection. And that's going to be a distance of 18.3 meters plus 69.4 meters, and then so it's a plus 16 meters. So you have to travel all this distance, but you're going 60. Well, now we got to divide by our velocity. 16.7 meters per second. Second pops upstairs, and we get our time for that. And then that's going to be 18.3 plus 69.4 plus 16. Divided by 16.7, and this is going to be 6.2 seconds. Alright, so I might actually have to take a pause here, because I just need to check my answer. We didn't even do any, like, we basically just did this. The second problem, it said, you know, where, as a city traffic, you expect cars to be cautious, consumer reaction time, find the length of time the yellow light should remain on, using a braking acceleration. So I would say 6.2 seconds. And this is the point where this problem might be in the back of the book. So I'm going to go check that and maybe, you know what I mean, just recap this problem. And I see there's 3 things here. I'm kind of confused where they got the 3 things. We'll see if, well, we kind of saw where we got 3 things. So we're going to see if that matches up. Alright, catch you on the flip side. Alright, hell yeah. Now welcome back, because I think I found an error in this equation. Okay, because the question says a yellow light has to stay on long enough to allow the driver to get through the intersection, or the second they see the yellow light, stop before reaching the intersection. So these aren't, see this equation right here, they tried to make them equal to each other where they're not. It's a whatever's faster, you know what I mean? So we're just saying, well, I don't know, because it's saying, well, using this acceleration, deceleration, okay, yeah, fair enough. There might be some. So you have to say, hey, what's going to be the average, you know, deceleration of a car? You know what I mean? Once you do have that reaction time, yeah. So let's just say this is the, hey, this has a margin of error, of a factor of safety. It's real easy to slow your car down 2 meters per second. It's kind of like 5 miles an hour every second. Every second I should be able, so 5 seconds, 25. 20, 15, 10, 5, 0. Okay, fair enough. But yeah, because what did I get? I said 6.2 seconds. That's how long it should stay on. 6.2 seconds. But then their answer was 10.52. And they say, you know what I mean, for this, use this stopping distance from the problem that we did before. And that stopping distance was our initial velocity times our reaction time, because we're not going to be braking through here. We're just going full speed, and we're going 16 meters per second for about 1.1 second. So you know what I mean? So yeah, so we got that. That's like 16, 17 meters. And then we're going to add, but then if we did throw on the brakes, it's going to take a while. Like I said, our acceleration is -2 meters per second every second. And we're already at a speed of 16. So it's basically going to take approximately 8 seconds to slow down. And so the time factor right here is, this is basically the change in time for acceleration. And I do show that. Because, yeah, initial velocity times reaction time, hell yeah, that's just cruising. But now, this initial velocity is squared divided by 2 over a. You know what I mean? What I did was this initial velocity divided by 2, that's that component, multiplied by the velocity over a. And if we come down here and write it again, you bring the negative sign in there. And then this velocity initial, why the negative sign? Well, because we were, it was velocity final minus velocity initial. Velocity final was 0. So this basically is change in velocity. So even though it's just a one number unit negative velocity initial, V naught, it's change in velocity divided by a, so we identified that. And if we identified that, we know that our equation 1, acceleration is change in velocity, change in time. Oh, we have change in velocity divided by acceleration. Bring that. So this is basically the change in time for acceleration. So that's how this whole component right here is change in time acceleration. And if we started at 16 meters per second, ended at 0 meters per second, our velocity average is 8 meters per second. So that's why this is V naught divided by 2. So yeah, so just going over that one again, so you kind of have it in your head. Hell yeah, we're doing good. And perfect. So now what they wanted to do for the time, and I guess I can go just right back here. They said your reaction time. So the time for the light should be your reaction time. Okay, fair enough. And then it should be this V naught over 2a. You know, and they write it so crazy again. You know what I mean? It should be just plus V naught over 2 times change in time for the acceleration. There you go. And because this will become a positive because your acceleration is -2. So these two kind of cancel out. But you can just write it like this. V naught over 2 times the change in time. But to actually get the change in time... Oh, now I'm losing my mind. I think actually I just said, okay, I just went with it. No. This whole thing is your stopping distance. So if this is your stopping distance, then your time. So this whole thing is your change in time for acceleration. I don't know. This is the acceleration component. This is like the deer in the headlights, your reaction time. But anyway, this whole thing is, oh, so the change in time component of this is 1.1. The change in time component of this, I guess I didn't do it. I guess you'd have to come over here. Ah, bummer. I guess I wasn't, I mean, the change in time component is V naught over 2A. It's just not in a form that I like looking at it like that. But I'm all right with that. Oh, yeah, because all they did here, you know, our problem, acceleration, change in velocity, change in time. And then so change in time is change in velocity over A. Our change in velocity, though, is, I guess, half our initial velocity. Oh, bummer. Alright, that wasn't even what I was getting at. But anyway, I'll have to relook at that. But anyway, just writing it in, you get 1.1 plus 4.16. And then just plus the stopping distance. So this is where it gets crazy. Because the car sees the light, has a reaction time, and then slows down and can stop before the light. So now, what distance is that? You know what I mean? Because like if or what time, or I guess what I'm saying maybe is this time component right here is 4.16 plus 1.1. This is 5.26. Holy Toledo, it's the same. It's the same. So alright, well, let's slow down and just do this one. So we have the change in time for the light is a reaction time 1.1 minus V naught 16.7 divided by 2, negative 2, plus our distance from before. So this was, oh, this is the distance of the intersection. So that's just 16 divided by 16.7. Oh, that's probably why I got this one totally wrong. Yeah. Oh, okay. Never mind then. 16 divided by x. Yeah, so this is 0.96. 1.1 plus, because this is x divided by 4. So this is 4.16 plus 0.96. 1.1 plus second answer plus 0.96. Hey, it's a 6.2. Now, is that kind of what I had? Okay, holy Toledo. No. I thought they were adding the entire stopping distance again. But no, this is just the distance for the interchange. So, no, I'm glad that they didn't. Because, I don't even know how to talk my way through this one. I only have a minute. But yeah, because if you were right here, this is your reaction time, 1.1 seconds. And if you threw on the brakes, you would get to here. Okay, fair enough. So that's how long the light, you know, could be. Oh, no. But if you're just minusculely in here, that's the interesting. This is why you have to add the time it takes your vehicle to go full speed. Well, no, I don't think so. I'm going to relook at this one. Because if you're right here, I got to add more time on the clock. Let's just do it right now. All right, more time's on the clock. And we're going to turn that off. Okay. So, let's look at this. If you're right here, the light turns yellow, and you want to brake. You have 1.1 seconds of reaction time. You throw on the brakes. Your acceleration takes you for another, you know, you're stopping. Your acceleration takes you for that distance. Which is 69.4. Yeah. So, which one's 69.4? Yeah, that's E. Meters divided by your velocity, but it's divided by your velocity in half. So okay, so this is the V naught divided by 2. Because if you do want to slow down here, it's not just V naught divided by the distance, because you're going to be at your V naught there and you're going to be at 0 here. So you're taking your V average. which is, okay, fair enough. And that's going to be 8.3 seconds. Wait, no. Wait, how did I get to 0.62 seconds if that's actually 8.3? Oh, this is interesting. Because, oh, this is fascinating. Oh, this is exactly why yellow lights are a son of a bitch. Because they're hard. Like, it's like the second you want to stop, you're just like, dude, I don't want to stop. But it won't give you enough time. Because, no, I mean, that's interesting. Okay, so, no, this is interesting. Well, let's talk it through. Yeah, because, holy hell, how long does it take to actually stop your car? It's going to take a hell of a long time. It's going to take 1.1 seconds, plus the distance it takes your car to slow down, which we said was that. Yeah, so this is the distance that your car has to slow down. And yeah, so that's, again, it's a negative x squared, divided by 2 times negative 2. Alright, times negative, answer. Oh, oh yeah, and yeah, so that's the distance. That's the distance that your stopping distance is 70 meters. And the time it takes you to stop, you have to use the V average. So you have to take this divided by your x divided by 2. Yeah, it's 8.3 seconds. Yeah, it's going to take 8.3 seconds. So, plus 1.1. So, it's going to take you 9.3 seconds. So, I mean, you're going to be almost stopped right here, and that light's going to turn red. Because it's going to be, if you're right here, you can stop. That's the crazy thing. You can stop, but it's going to take you 9.4 seconds to actually stop your car. Now, right at this magic point that they chose, you know, if you're just like, no, I don't want to stop at negative 2 meters per second, you know what I mean? That's just why you don't want this to be a jarring deceleration. This is why yellow lights probably should be on for a little bit longer. Or just have smarter intersections. Man, I don't understand why intersections are so stupid. I mean, with all the, I mean, you can't just see the car coming. I mean, this is 2023. Holy, I mean, talking about, you already have like AI vehicles that can navigate the entire United States, but you have a traffic light that's just dumbass. It's so dumb. It's like the second you get close, it's like, nope. It's like, not today. Not any day. Not any day. They're never in your favor. It's crazy. Okay, but that's why this takes 9.4 seconds. But if you're at this magical spot where you can actually stop, and you choose not to, I mean, because if you're just like right here, if you're just like 1 meter on this side of it, how long is it going to take you to go the speed limit and get your friggin' vehicle all the way through? And it's crazy because you also have to add the length of your vehicle. So the length of the vehicle, another couple meters, isn't actually into this equation. Because you can't just get to right there. You have to get your vehicle through the intersection. So your vehicle's 2 meters. Yep. So we could add that in, and maybe this is 6.3 seconds, but boost it up a second. All right, let's do it. And I don't mind working small because now it's just the concepts of just like, holy hell. Yeah, so you are way the hell out here, and that's alpha E. That's alpha D. You know what I mean? That's 69 meters plus this 18.3. Your reaction time is your initial velocity, which is 16.7 times 1.1. So that's your 18.3. Here's your 70, and then your intersection 16. So alpha D plus 16. This is your 103. You're 103 meters away, and you're going divided by that 16.7 meters. It's 6.22 seconds. So, yep. So that's how long this light just has to stay on. But let's say it's 103 meters plus 2. 105. Let's say it's 105 meters. How much does that change the light? Because you got to get your whole vehicle through. So I guess I thought there was a huge glaring error in this problem. There wasn't. That's usually the case. When you're ever just like, oh, hell yeah, this problem is totally wrong. It's usually not, because they're textbooks, and they can always revise them. And you have like thousands of smart kids. Well, you know what I mean, a smattering of smart kids, but 1,000 kids actually doing these problems. Okay, and then divide by x. So it's 6.35 seconds. So I would increase this by 1.5 seconds. You know what I mean? Oh, no, just 1/10 of a second difference. But friggin' A. Alright, so we did it. Man, that was a conundrum. I just don't like problems. Look at this. V0 over 2a. That just negative. You know what I mean? And how that negative, it should be positive. V final minus V0 all over 2. And then multiply by 1 over a. You know, I don't know. But anyway. Okay, friggin' A. I guess we got the answer right, but I'm glad I double-checked. But holy Toledo. So this is real time, I guess. I mean, how else do you do a problem besides just crunch through it? And it's real hard to actually make a video of yourself doing this crap. My goodness. It's real easy just to spend the half hour, go through the problem, and then figure out, alright, yeah, curtain call. And then figure out, you know what I mean? Just write the stuff that makes sense. Which, there's not much on this page. So that would, I should make videos like that too. But I do really like making videos start to finish, because no one does it. No one says, hey, I want to do this problem. I'm going to turn on the camera, and I'm going to try to figure it out. You know what I mean? And here was the mustard and mayonnaise of our problem. And hell yeah, we did it. Alright, thanks for joining me, and guess what? That's a video.